Hey everyone, hope everybody's doing well. Today I'll show you how to do support vector machine classification in Rattle. For this exercise, you're going to be needing the audit dataset, which is again another built-in dataset within the Rattle environment. Just simply load the data and make sure that the ID variable is set as the identifier. Other variables are set as the input variables, the ignore accounts as ignore, and risk adjustment at risk, and also target adjusted as the target. Now, if you wish to set any other variables as ignore, you could simply do that, but make sure that you have enough input variables to be able to build models, to build classification, SVM classification for our target adjusted. Now, just a reminder as to what this target adjusted is actually about. And if you've seen in previous labs, essentially the target adjusted is looking at pretty much a bunch of features, bunch of variables to predict whether a person is required to be audited or not, or is required to, or money is required to be recovered from that particular case or not. For every associated, I guess, ID, or for every associated person in this data set, whoever has a higher or has a more than zero risk associated with their record, then obviously we also have a target adjusted of 1. Now you can explore this by yourself, but essentially this audit data set is all about, as we've talked about in the past, this data set is about identifying the cases that are required to be investigated, and they are required to be actioned in order to recover money. So how to build SVM, just make sure that the partition is also ticked. How to build SVM models or support vector machine models, you simply go to the model tab and make sure that the SVM is clicked. And now you'll see that there are two main parameters that you can change. The first one is the function that we use to build the SVM, and there's a bunch of them. And each has its own way of obviously building the support vector machine. But each has its own performance. And at some point, I'm going to show you how to actually look at multiple functions, multiple kernel functions to be able to build the best or the most accurate model for your case. You could also change other parameters by typing, for example, the cost associated to the KSVM function. You can get more information by clicking at this link, which takes you to the Rattle documentation about the SVM, especially about what you could put into the options box. At this stage, the cost associated with building a model is set at 1. Again, have a look at this documentation. It'll explain what this cost is actually about. It's actually a trade-off. It's a cost or a trade-off cost in terms of the error and also in terms of building the model. Now, if I want to build this model, let's just stick to the default parameters. So I simply click execute, and I've got my summary output. So it's using the KSVM, and the cost is 1. Like I said, it's the default function or the default parameters, and the function that we used is radial basis kernel function, and we have about 583 support vectors out of 70% of the data that we have. So if you remember, the data set includes 2,000 observations. So 70% of that is about 1,400 observations. So 583 support vectors for those 1,400 observations. Now, if I want to see how good my model is performing, essentially I go to the evaluate tab and make sure that the SVM is ticked, and I click execute, and I get about 14.8% overall error and average class error of 26.85%. Now you may get other values, and that depends obviously on which one of these variables you've set input, or which ones you've already set at ignore. Some of you may have already set the risk adjustment at ignore, which is fine. But essentially, we need this risk adjustment to be set at risk for following exercises. So if you get a different measure, that's okay. That's the whole idea, that based on the data set that we have, what is the overall error rate at that given time, at that given given point. Now you can also build that for the testing, and you will see that the testing has higher overall error rate compared to validation testing. You can also go back and build the SVM using different functions, for example, polynomial function, and see what the difference will be. So if you go to the evaluate tab and look at the validation, we will see that the overall error rate is now decreasing. The previous one was about 14.8%. Now this one is 13.5. Again, you can go back and build using linear model and go back to the evaluate, and you will see that it's also about 13.5. So you can do this. You can experiment with multiple other functions to see which one is giving you the better performance. Now, what we want to do is, if I go back and build the default, what I want to do now is I want to build a decision tree just to check or to compare the performance of the two models, whether the decision tree is giving me a better performance versus a kernel function or SVM. So in this case, if I build my decision tree, I go to the evaluate tab and make sure that both SVM and also the decision tree is ticked. And you will see that for the decision tree is about 15.4% versus the SVM model is about 14.8%. So based on just those two measures, I can see that the SVM model is performing a little better than my decision tree. Now, you can also do this for other kernel functions. You can look at other functions and see which one is giving you a better performance. Now, remember, we've just done one for example, polynomial, and it had 13.5%. So obviously that 13.5% is much better, much more accurate than the decision tree. Now you can also look at for example, other measures such as the ROC. So if you remember, this gives us the area under the curve. And if I build one for my decision tree and another one for my SVM, you will see the performance of the two models, which in this case, the audit table, the SVM for the audit data set is giving me 89% versus area under the curve for decision tree is about 84%. So obviously SVM is doing much better in terms of performance or in terms of the area under the curve. Now, the last thing I want to talk about is the risk charts. Again, you can have a look at the documentation. It explains everything that you need to know about the risk adjusted variable. Essentially, what you want to do is risk, or this is mostly used for risk analysis, and it gives you an indication as to which model is performing a little better. So again, this is just purely based on the risk analysis. So you will see that for the SVM, I have 84% versus for decision tree is about 80%. Now, again, you can have a look at the documentation, and we will talk about this in further detail in the lab. But essentially what risk adjusted or this graph actually talks about is, given a certain number of caseloads, for example, certain percentage of the caseload, let's say 20%, how many of my observations require actioning and how many cases we are actually going to, we are able to recover. So again, remember, in terms of target adjusted or in terms of the observations we had in the data set, how many of them you're going to be able to recover from the people that we need to investigate or we need to action from all those cases. So for instance, with 20% looking at only 20% of the data or the caseloads or all the cases in the observation, how many will return us or how many of them we can sort of recover, which is about 72% as an example. Overall, it's about 84%. It means that if we only action 84% of the cases, we're going to be able to recover all 100% of the cases in our data set versus 80% in the decision tree. So I'm going to leave the analysis bit for you to do and to understand what it actually means. Is it actually a better performance to have a lower levels of risk adjustment or risk chart between decision tree and the SVM? I'm going to leave this for you to sort of do and think about, and then we will continue this discussion in the respective lab. Again, I just wanted to show you how to do the SVM, how to build different models, how to evaluate them, and what button essentially to tap and what button to choose, and how to build the risk charts for both for both the SVM and also the decision tree. You can do this for other models as well if you wish to, but for now, for this exercise, we are just going to stick to the decision tree and also the SVM. This is it from me. Thank you again, and I will see you in the lab.